copper-catalyzed azide-alkyne cycloaddition became one of the very widely used reactions. We reported it for the first time in 2001, 2002, but the mechanism of that reaction was not really studied very carefully until some of the recent years. The reason is it found many applications because it was simple to perform, but what appears to be simple in a chemical sense and is usually staying as a black box for end users, just as you don't know what's inside the computer, you don't know how all the parts and pieces fit together. All you care about that the computer actually works, that the screen is showing everything what you are typing, that it calculates what you are asking it to do, and so forth. The same thing is true for chemistry. But as chemists, of course, we need to understand how exactly chemical transformations happen. And study of the mechanism and the reaction of organic reaction mechanism, especially of a multi-step reaction mechanism, is not a trivial thing. Because we can propose and we can find very intellectually challenging, intellectually sophisticated ways of describing how the molecules behave and how they look. But in reality, molecules, of course, couldn't care less how we describe them. They behave as they do, and it becomes our art and our intellectual ability to be able to interrogate and to understand precisely what the chemical system is telling us. So in this case, back in 2003-04, we published our first papers on the catalysis on the copper-catalyzed azide-alkyne cycloaddition, and looking at the catalytic cycle shown here on this slide. As you see, it's a very logical, very reasonable, goes circularly from, clockwise, left to right, and it makes sense, and it's eye-pleasing in general, except it's not very complete. There isn't anything wrong about this chemistry, but it doesn't account for everything. And of course, as I mentioned, we are showing some single bonds, double bonds, triple bonds, which are all formalisms. They are not in a reality of interaction of a metal with, for example, acetylene. There are many different ways how we reduce complexity to make it more understandable to us, but also being able to dissociate from that. That would be an important thing. One of non-chemistry slides here, and how brain can play very many interesting tricks on us. It's, this art, this sculpture, I took a picture of in Norway a few years back. And these are normal faces. They are made out of masks, rather. They're made out of cast iron. And when you look at them, you don't really notice anything unusual. But if you look in profile, you will see that they're actually convex, not concave, not convex. So they are going the other way. If I flip it back to you, they start looking normal again. In reality, they are not, we haven't done any photoshopping or anything with them. So it's purely the trick which is happening in your brain. We can continue doing that many times, and every single time I do that, we would still come back to those faces. They look the way they should in a normal way, because that's how you know people look. There is no face which looks in a different way. And this is one of the illusions and optical illusions which has been used for a long time as well. It's called the hollow face illusion. It's a mask of Charlie Chaplin, and normal papier-mâché or plastic, you can even do it at home yourself. And you will see that at some point, if everybody is different, again, there is no trick here. It flips around and it looks at you again as if it was actually going the other direction, as if it was actually looking the other way. Again, there is no trick here, there is no photoshopping or any computer manipulation. It purely happens in your brain. So does chemistry. So what we draw on these slides and what we show on these pictures is more or less, what actually purely, a simplification which is convenient for us to understand the reaction mechanism. In this particular case, there are many different reactions, many different side processes which are dictating the state of the catalyst and which are controlling how the reaction is proceeding. Without knowing them, we cannot control the reaction, we cannot make it more user-friendly, we cannot use it for study of those biological systems. And for example, we can form different catalytic species, as I mentioned to you, from the acetylenes. The ones which are shown here, the acetylenes which are the aggregated ones, are the catalysts which are the reactants, I'm sorry, actually, they're off-cycle species which are not catalytically active and which are inhibiting the catalysis. If you imagine the high concentration of the acetylene, you immediately move all of your catalyst off-cycle, so it will slowly bleed into the catalytic cycle. And it will control the rate of that reaction, so you would want to avoid that in general. There are also some side products which can be formed in these reactions and these transformations, which are which are affecting how fast it's proceeding, even if they are not part of the catalytic cycle at all. So in general, when we look at the rate of the catalytic reaction or multi-step reaction, we can always express it in terms of the rate of the formation of the product, or in terms of the rate of the consumption of the reactants. And the general rate law in this system would be catalyst to the power C, and which is called the order of the reaction, the reactant A, reactant Z to their corresponding powers, and understanding whether those reagents are actually figuring or becoming part of the rate law in the first or second or zeroth order is very, very important. It's critical for the improving and for using the reaction in different settings. Because as you can imagine, if our both reagents are involved in the first order in the power of 1, and the concentrations are low, they're, for example, 0.01 molar or so, as we could move at the lower concentrations, the rate of the reaction is going to be very, very small, very low, and we will never achieve full conversions in a, for example, in the second order reaction, the reaction shown in red here. Over 100 minutes under this, or 1,000 minutes actually, under these conditions, these simulated conditions, the conversion only achieving about 20%. Whereas in the first order reaction, we can get it all the way to the 100% conversion, so meaning we can quantitatively label our biomolecule, for example. So how can we study those complex reactions which involve many different intermediates and potentially involve off-cycle events by methods which are available to us these days? So ideally, of course, like I said, we would like to be, just as we would be in the biological system, we would like to be part of that reaction and study it under synthetically relevant conditions, exactly how you would perform it in the flask, without changing too much the state of the catalyst or without affecting it at all, ideally. And but those are the complications which we don't really address in the, well, and don't really study even at the university level, because most of the time we'd like to reduce complexity and we don't want to solve equations with too many unknowns because it becomes too complex of a system to handle. But numerically, these days, we can handle very large data sets. We can collect data on every second on a reaction using, for example, in situ IR monitoring, infrared monitoring of certain peaks, or reaction heat flow colorimetry, a technique which allows you to measure the heat flow which a reaction is producing. And in the studies of catalytic systems, it becomes particularly productive, particularly useful tool. It has been used by industrial chemists for quite a while, and in academic setting, it was introduced by Donna Blackmon, my colleague at Scripps now, who used it in part for reaction progress kinetic analysis. So what it allows you to do is to study how much heat per unit of time is produced in any given reaction. And if we know how much heat is produced, most of the reactions we study exothermic, we would know what the rate of the reaction is. We don't need to take aliquots and study them, in the dC over dt way, and to fix one of the reactants in a very large excess, not to affect the its concentration throughout the reaction. Also, we can study the reaction all the way throughout its course. It's not very difficult, and every single point in this system, in this red curve, is a data point. So in 60 minutes, we can easily obtain 600 points if we wish to, and we can process them to obtain in several experiments. It doesn't always go as smoothly, but we can obtain in several experiments a lot of information about the reaction, such as how long it takes to get to the high rate, what the reagent order is, how long it takes to go to completion, and so forth. What we did with our studies here in that, looking at the understanding of the catalytic azide-alkyne cycloaddition, is we started started with different kinetics experiments in the beginning, but most recently used stoichiometric chemistry of the copper acetylides, which are well defined. I told you about the acetylides, which are usually polymeric and not well defined. The acetylides, which we are showing here with N-heterocyclic carbenes, are very nicely behaved mononuclear non-polymeric acetylides, and we were very surprised when we introduced it in the reaction and we did not see this reaction to proceed at all. It was completely silent, even though we had the whole equivalent of our reactive intermediate, of our copper. If we introduced a second copper in there, a second copper atom in there, reaction proceeded almost instantaneously. It converted to the product within 10 minutes. And it doesn't really matter what copper source you are using, as long as it is not any source of the copper-1 catalyst. So when we started looking a little more deeply in it, using different copper isotopes, which effectively allow us to color different copper atoms in different colors and track where they go in the reaction process. Thankfully, copper 63 and copper 65 are two natural isotopes of copper which can be obtained from not from different facilities, and they give unmistakable mass spectrometry signature. We were surprised to find that one-to-one scrambling occurred and our copper isotopes got incorporated into the product, into the one-to-one ratio. So what it told us in the end, that two coppers are absolutely required, of course, in this chemistry, but also that we very often, well, not very often, I'm sorry, that we can define the role of those two copper atoms as completely independent, although in the end they end up in the same place. So here is an example of a multi-center reactive intermediate which we have never seen, we've never isolated, but we know that it exists because we need to obtain the product from it. And the reason it exists, and the reason we know that it happens, is that it does have certain lifetime, because those ligands, those coppers, need to become equivalent. It happens after the first carbon-nitrogen bond is formed, which is a true oxidation event, when one of the coppers is becoming more electron deficient. But again, that's just our rationalization. We calculated and did computational studies on it. It does make sense. But much more important is what we learned in practical terms. In addition to uncovering new fundamental reactivity of copper acetylides and increasing their reactivity with the nucleophilicity, we also learned, and that's what we are pursuing now, that many different acetylides and acetylene derivatives, not necessarily of copper, can be used in this chemistry. And this reaction becomes merely a litmus test, an indicator of the different reactivity manifold of copper acetylides or reactions of acetylenes in general catalyzed by copper atoms. The applications now which we are able to do with those new acetylides and new chemistries span everything from material science to biological studies, because now we can control the rate from a completely different vantage point and get a very different leveraging of the reaction rates and reaction efficiencies.